beta be a basis for a topology tau on X. So that's mean we are saying that beta is a topology and that beta, that basis generates the topology tau. Okay, you can say generates here, you can use the topology. Okay, now then we prove that tau equals the collection of all unions of elements of beta. So we will prove this one. Now this shows that tau is unique. That's mean whenever you have a basis and whenever you have a topology generated by that basis, then that tau should be equal to the collection of all possible unions of elements of beta. Okay, that statement is understood, right? That's mean we take all possible elements of beta, take their union, all possible unions, and we have another collection, right? Now we say that tau is that collection. Okay, and obviously that collection is unique because we are taking any number of elements of beta and we are taking that union. Okay, so that collection is unique. So here is the proof. So first of all, let tau dash be the collection. That's when tau dash, it is the collection of all unions of elements of beta. Okay, and we claim that tau equal to tau dash. Now how to prove that tau equal to tau dash? So that's mean we will show that tau, since both are sets, so how to set the, how to prove that two sets are equal? If we show that this subset of this and that subset of that, then that is done, right? So now first we prove that tau dash subset of tau, and then we prove that tau subset of tau dash. Okay. So let U belongs to tau dash. Okay. U belongs to tau dash. So what is tau dash? Tau dash is the collection of all unions of elements of beta, and U is such an element. So then this implies actually just by the definition of tau dash, U equal to union of some index set B alpha, where B alpha belongs to beta, right? Okay. Now tell me one thing, you know that base a topology generated by a basis. Now from that definition of topology, can you see that each element of the basis is also element of tau? That's mean beta subset of tau. Can you see that? Yes. Yes. Hello. Can you see that beta subset of tau?
Yes, sir.
Yes, it is
Yes, sir.
it is trivially, right? Trivially beta subset of tau. Now since beta subset of tau, so that's mean each of the element B alpha belongs to tau as well. Tau is the topology, right? Now each B alpha belongs to tau and tau is a topology. And so by the property of topology, we know that then union of B alpha that belongs to as well tau, right? Why? As tau is a topology, right? And that is my U. So we have taken U from tau dash and we got U belongs to tau. So that implies tau subset of tau dash subset of tau. This proves this. Is that part clear to everyone? That is simple, right? Okay. Now we do the reverse one. So we show that now tau subset of tau dash. We will show that. So now let W belongs to tau. Okay. Now what does it mean by W is an open set in X, right? And by the definition, that's mean for each X belongs to W, we should write that W. There exists an basis element Bx such that X belongs to Bx subset of W. Right? This is clear, this definition. Right? This is just a definition of the topology, right? How? So we know that W belongs to tau is if and only if, right? That for each element of this one, so there exists a Bx such that X belongs to Bx subset of W, right? So that is the definition of open set. Now this implies W equal to union of all of these Bx where X belongs to where? X belongs to
W itself.
W itself. This one, right? So if we take W belongs to tau, we get W equal to union of this Bx where Bx belongs to beta. So that's mean W is an elements, right, which is union of elements of beta. So that implies W belongs to tau dash. So therefore, since that's mean so tau subset of tau dash. Now why this is? Because of this definition. You can look at the definition of tau dash. So
So,
tau dash is the collection of all union of elements of beta.
so how
Right?
we deal for the empty set, taking union over nothing?
Right. Taking union over nothing. You can take your index set is just your null set.
Okay, so
Okay. Fine. So this is done. So that's mean we have proved that tau equal to tau dash. Fine, right? So that's mean we have given the answer of this question. That is, if beta generates a topology, then the topology is unique. In the sense that that topology is actually the collection of all unions of elements of beta. Okay. Now come to the next question. What you also asked last time in the last class, that if you have a uh, topology, then how to generate a basis? Now this is the first question. And the second question is, if you have a topology, now if you have many bases, then can you say that all the bases are unique? That's been basis. Since we know that if a basis generates a topology, then that is unique. Now if you have a topology and if you take a basis, is that unique? That is the first question. And even if it is not unique, can we say that all the bases have same cardinality? So these are the two questions. Now I think you already know the answer of these two questions. So can you quickly give me the answer? So first question is, if you have a topology, is the basis unique? This is the first question. And the second question is, if you are given a topology, all the cardinalities of basis are same. That's mean the cardinality of the basis is also in kind of unique number. What can you say about that?
Both are wrong.
Both are wrong. Good. So can you give me just a quick example? Both are wrong.
सर जैसा आपने सर दिया था पिछले क्लास में एग्जांपल कि सर यूजुअल टोपोलॉजी के लिए हम
Right, that collection of open sets, open intervals लेते A, B, right? Where A, B belongs to R, this is an uncountable set. That is also a basis. And if you take A, B belongs to Q, that is rational number, then that is also a basis. And one is countable, one is uncountable. So that's mean it is not same. In fact, their cardinality also may be different. Right?
Yes, sir.
Right. Good. You remember that. And now we prove the next lemma. This one. So how to generate a basis from the topology? Okay. So let X tau be a topological space. Okay. Now let beta be a collection of open sets of, we can say this, open sets of X, or in the sense we can say that beta is a collection of elements B from beta, okay, with the following properties.
Sir, it should be tau.
Sorry. Good. For each u belongs to tau, for again each x belongs to u, there exists a b, you can say bx belongs to beta, such that x belongs to bx subset of u. Okay. Now then beta is a basis for the topology tau. Okay. That's mean, suppose you have a topology. That is mean x tau is a topological space and tau is the topology. That's mean tau is the collection of those open sets. Now, if we take a smaller collection beta in such that, that's mean smaller collection of open sets. That's mean tau has many open sets. We are taking only few particular open sets in such a way that whenever we have choose any open set in tau, okay, and if we choose any x from u, then there exists a basis element, that is mean that there exists an element from beta such that x belongs to bx subset of u. Okay, then beta will be a basis and that beta generates the topology tau. Okay, so that's mean what we are saying that हमारे पास टाउ एक टोपोलॉजी है, इसमें बहुत सारे ओपन सेट्स है, तो हमें सारे के सारे ओपन सेट्स नहीं लेना है, हम क्या कर सकते हैं कि पार्टिकुलर कुछ ओपन सेट उससे ले सकते हैं, ऑब्वियसली इनफाइनाइट ही होगा, सो दैट कि वो जो अभी जो स्मॉलर कलेक्शन है बीटा, दैट्स मीन बीटा इज अ सबसेट ऑफ एक्चुअली टाउ, ठीक है, ये प्रॉपर सबसेट्स लेंगे जनरली, तो ऐसा हम प्रॉपर सबसेट लेंगे कि कोई भी अगर एलिमेंट हम यू से चूज करेंगे फॉर ईच यू के लिए, और उस यू के अंदर कोई भी एक पॉइंट के लिए हमारे पास हमेशा एक एलिमेंट रहेगा बीटा से, सो दैट ये प्रॉपर्टी होल्ड हो जाए. ओके, अगर टाउ के कोई भी एक सबसेट ए प्रॉपर्टी होल्ड करता है, देन हम बोलेंगे, हम प्रूव करेंगे एक्चुअली, देन बीटा फॉर्म्स ए बेसिस एंड इट जनरेट्स द टोपोलॉजी टाउ. Okay, it is simple. Okay, now here is the proof. So first we prove that beta forms a basis. We have to first prove that, okay, because we do not know beta forms a basis or not. So first we prove that beta forms a basis, and then we prove that that basis generates the same topology tau. Okay, so we know what are the two conditions of basis. So let's check the first condition. First of all, take x belongs to x. Okay, fine. Now since x belongs to x, what does it mean? We know that x belongs to tau, right? Because हमें पता है कि x tau में रहता ही है whole set. Okay, so that's mean यहाँ पे जो है इस u के बदले में हम x को रिप्लेस करेंगे, क्योंकि ये प्रॉपर्टी तो सेटिस्फाई करना ही है, right? That's mean for each element x, so हमें यहाँ पे x भी लिया x से, ठीक है? So there exists a, then by the given property, so there exists bx belongs to beta such that x belongs to bx. Okay, so that's mean for each elements of x we must have an element beta such that x belongs to bx. So first property of basis is satisfied, right? Now we prove the second property of basis. So let x belongs to b1 intersection b2, where b1 comma b2 belongs to beta, right? And which is subset of tau, right? Now since b1 and b2 subset of tau, that imply b1 intersection b2 is also belongs to tau, right? So beta 1 is open set, beta 2 is an open set. So therefore b1 intersection b2, it is also an open set, right? Now again, now here for each tau, here for u we replace b1 intersection b2, right? And so we choose any element x. This is my x, and here we will choose some b3. Then we are done actually. So again, then by given condition, there exists b3 belongs to beta such that x belongs to b3 subset of b1 intersection b2. So the second property of basis is also satisfied. So thus beta forms a basis. Any doubt?
सर फर्स्ट पार्ट एक बार दोबारा बताओ.
ये वाला पार्ट.
यस सर.
ओके, तो इसमें एक्चुअली क्या प्रूव करना है? हमें बेसिस का फर्स्ट प्रॉपर्टी प्रूव करना है. तो बेसिस के दो प्रॉपर्टी है. क्या क्या प्रॉपर्टी है? फर्स्ट प्रॉपर्टी है कि कोई भी अगर एलिमेंट, कोई भी अगर पॉइंट लोगे एक्स से, मतलब होल स्पेस से, देन उस एक्स को कंटेन करके हमेशा एक विशेष एलिमेंट रहेगा. ठीक है, ये हमें प्रूव करना है. तो क्या एक हम कैसे प्रूव करेंगे? फर्स्ट ऑफ ऑल हमने एक चूज आर्बिट्ररी एलिमेंट लिया एक्स फ्रॉम कैपिटल एक्स. तो हमें पता है कि एक्स टाउ में तो रहता ही है, मतलब एक्स इटसेल्फ इज एन ओपन सेट. सो ये जो प्रॉपर्टी है ना, इस प्रॉपर्टी हम यूज करेंगे, ये प्रॉपर्टी, और इसमें u के बदले में हम बस x ले लेंगे, कैपिटल x. So इस प्रॉपर्टी से हमें इंश्योर मैं होता हूँ कि कोई भी अगर x के लिए मतलब अगर कोई भी एलिमेंट होता है स्मॉल x जो कैपिटल x में है, सो देयर एग्जिस्ट है bx मतलब बीटा से एक एलिमेंट रहेगा, so that x belongs to bx subset of u. That's mean here x belongs to bx subset of x. बट हमें एक्चुअली चाहिए ए वाला ओनली, x belongs to bx, यही चाहिए था हमें, तो ये मिल गया. This is the first condition of basis. First condition of basis means whenever you have any element from the space x, then there should be a basis element containing that set, that point. So we are done.
Got it.
Okay. Okay. Now we prove that. Now this is the basis. Now basis generates a topology. Now we prove that that topology is same as this topology tau. So let say tau dash be the topology generated by the basis beta. Okay. Now we claim that tau equal to tau dash. We will prove this one. Okay. So first of all, let u belongs to tau. Okay. Now u is an open set, right? So therefore we can say that. Okay. So first we need to prove that tau dash is in that subset. Right. That part actually is trivial. Okay. Okay. We take u belongs to tau. Then for each x belongs to u, there exists a not, we should not use that basis element. Element b such that x belongs to b subset of u. Okay. This is again from the given condition. See, that was my given condition. So what is my beta actually? Beta is a collection of the open sets such that whenever we have any other open sets from tau, then for each element x, there exists a bx such that this property holds. So x belongs to bx subset of u, right? Now we are using this one only. So first we take any u belongs to tau. Therefore, by the construction for each x, so there exists an element. You can write bx as well from beta such that x belongs to b subset of u. Okay. Now again, this is the definition of now this is the element definition of the tau dash. Remember that what is tau dash? Recall. So u belongs to tau dash if and only if there is the same definition actually. For each x belongs to u, there exists b belongs to beta such that x belongs to b subset of u. Right? That was the definition of a topology generated by a basis element. Do you remember that? Yes. Done? That is fine? Or are you confused about that? Say something.
Yes, sir, it's fine.
Right, you should speak, right? Otherwise, how shall I know that it is fine or not? So this is just a definition of tau dash, which is how to generate a topology from a basis. And we are using just the definition only. Now so tau, so that implies tau subset of tau dash. Now this part is actually simple. Now the other part is little bit tricky. Tricky in the sense that that is not trivial. You have to prove that. So now now W belongs to tau dash. Now again by this one, so that imply for each x belongs to W, there exists say Bx such that x belongs to Bx subset of W. Again by this one, right? Now that imply W equal to union of x belongs to again W Bx, right? Where Bx belongs to beta, which is subset of tau. Now again we are done. Why we are done? Because since now each Bx belongs to tau for all x belongs to W and tau is a topology, so that imply that union x belongs to W Bx, that will imply tau as well, and that is my W. So we assume W belongs to this, we get W belongs to this, so that imply tau dash subset of tau. So we have tau equal to tau dash. So we are done. So that's when both topologies are same. Okay. So this way we just prove first it is a basis, and then we can prove that it generates the same topology. So is that fine? This proof? That proof is simple actually. So first portion, that is tau subset of tau dash, that is very trivial, and only for tau dash subset of tau, that's one only need the definition. Okay. So therefore, if you have a topology and if you want to generate a basis, then the simple trick is that just take a collection of open sets so that it satisfies this property. So for an example, if you have some usual topology in R, if you take only open intervals, you can see that any only open interval serves this purpose. So therefore, only open interval forms a basis. Okay, fine. Now, if you have any question, you can ask. Okay. Now, for this, that is tau subset of tau dash, all of this terminology, we just want to introduce few terminologies. So first of all, that is one is finer. So what is finer? So let tau and tau dash. So first of all, we denote that here. So let tau and tau dash be two topologies on the same set X. Okay. Now then, if tau subset of tau dash, then we call that tau dash is called finer than tau. Okay. So tau is subset of tau dash, means tau dash is called finer than tau. That's mean the bigger one is called finer. Okay. And tau is called coarser than tau dash. Okay, the smaller one is called coarser and the bigger one is called finer. And similarly, we can use the strictly finer and strictly coarser. So if tau is proper subset of tau dash, then tau dash is called strictly finer than tau, and tau is called strictly coarser than tau dash. These are the just notations actually. Okay. So you have to just better to remember that which is finer, which is coarser. Finer means which is the bigger one, because sometimes it is it doesn't looks good to say that tau is subset of tau dash, right? It is always better than to say that it is coarser than this, or it is finer than this. It looks sounds good, right? So now I am going to prove one lemma, which is very important lemma throughout this course. So how to compare between two topologies, right? So obviously, if you want to say that this topology is finer than this topology, then you have to compare, right? But how to compare that? Because it has infinitely many open sets, it has infinitely many open sets. So how to compare between these two? Now there is a um, beautiful result actually. This way you can easily compare two topologies by in terms of their basis. Okay. So here is the lemma. I am writing lemma star. That's mean it is very important one. Okay. So first of all, let beta be a basis for a topology tau on X. Okay. And similarly, let beta dash be a basis for a topology tau dash on again X. Okay, so we have the same topology, same space X, and we have two different topologies, say tau and tau dash. Okay, and say beta and beta dash be a basis respectively. Okay, then the following two are equivalent. So first one is say tau subset of tau dash. That's mean tau dash is finer than tau. Okay, and the second is for each element X and for each say B belongs to beta containing X, there exists a B dash belongs to beta dash such that X belongs to B dash subset of B. So that is the very important result. Now you have to digest first. So when we say that two topologies are same or one subset of other. So when we say that this tau subset of tau dash, if first of all whenever you have any basis element B containing the element X, okay, then you must have a B dash such that B dash subset of B. Now sometimes people feel little bit uncomfortable because here tau subset of tau dash and here B dash subset of B. So it is one kind of looks like reverse, but it is actually strong one. Can you feel that? That is a strong one. If B dash subset of B, then actually tau subset of tau dash. Can you see that? Yes or no? See, if you have any doubt, you should ask now. Yes? Say something. I could not hear anything. Can you feel that? Yes or no? Or if you have any problem, just tell me.
Yes, sir.
Okay. See, actually the main thing is that whenever you have B dash subset of beta, subset of B, that's mean you can check that any element of B can be written as an element of union of B dash, right? So that's mean actually you can see that any elements, any open sets of tau will be some union of open sets of tau dash. So therefore that will be in tau dash. So this is the only trick. Now the proof is simple. So first of all we prove that say 2 imply 1. Okay, because that is the simple part. So let U belongs to tau. Okay, so that's mean U is an open set in tau. Okay, now we have to apply the basis. We know that beta is the basis for the topology tau, right? So therefore, for each x belongs to U, so there exists B belongs to beta such that x belongs to B subset of what? U,
U.
right? So this is the just definition of the topology tau and definition of tau and beta, how beta generates the topology tau. Okay. Now by the given condition, by given condition 2, so this one, so whenever x belongs to B, there exists a B dash, right? So there exists B dash belongs to beta dash such that x belongs to B dash subset of B, right? And we also know that B subset of U. So that implies you can see that for each x belongs to U, and this is subset of U. So there exists B dash belongs to beta dash such that x belongs to B dash subset of U. And that is the open set under tau dash. That implies U belongs to tau dash. Just apply the definition of open sets, right? So that implies tau subset of tau dash. So that is the proof. Is it not simple?
Yes, sir.
Yes, sir.
Okay. Now prove the second part. So 2 imply 1. Now this is also simple. Okay. Now given that
Sir,
tau, huh?
sir 1 implies 2.
Oh, sorry. Right. We have proved 2 implies 1. Now we prove 1 implies 2. So given that tau subset of tau dash. Okay. Now we prove that this set statement. Okay. So it start. So for each x belongs to x, let x belongs to b. Okay. Now what we need to prove that? We need to prove that there exists a b dash subset of b. Okay. Fine. Now where this b belongs to beta, right? What is beta? Beta is subset of tau, and also tau is subset of tau dash. So that's mean we have x belongs to b and b belongs to tau dash. So that's mean b is an open set in tau dash, in the topology x tau dash. So therefore we can just apply the basis element. Now since b belongs to tau dash, that's mean you can now treat that b as some kind of w, which is an open set, right? And x belongs to b. So therefore there exists b dash belongs to beta dash such that x belongs to b dash subset of b. So we are done. This is just this implies this, and ultimately you got the answer. Is that fine?
Yes, sir.
Okay, good. Okay, so this is the proof. 1 implies 2 and 2 implies 1. So that's mean now you know that if you want to compare two topologies, say tau and tau dash, what is the trick? You have to prove, you have to compare the basis elements. So take each basis element and this take another basis element, and if you can show that this, then you are done. And similarly by this lemma, you can actually prove also that if you take the basis elements, say AB, open interval AB, open interval AB, this one, when AB belongs to R, this, and if you take AB, AB belongs to Q, you can check that both actually generates the same topology. You can see here. You can choose one basis element here. You can find another basis element. This belongs to that. If you take this, then you will get this one. So by this approach, actually, if this is actually tau, if this generates tau dash, you can check that tau subset of tau dash and tau dash subset of tau. That's mean both will be equivalent. It is a simple one. Okay. Now we have some important topologies. Important in the sense that it is not important in general context, not in the other subjects, but important in these subjects only. Okay. So some important topologies on R. Okay. So first of all, if we take basis element in this way, AB, where AB belongs to R, then beta generates usual topology on R, right? Now that is the another one. Now if we choose the basis element in this way, say A, B, where A, B belongs to R. Okay. Now then beta generates a topology on R. Now this topology, can you say that this topology and this topology, that is 1 and 2 usual topology, are same? What is your guess?
I think second one is finer.
Right. Now this topology is called the lower limit topology on R. Now you should not forget that name, okay? The lower limit topology. Now in this way, if you define the basis elements, then this is called a lower limit topology on R, and we sometimes denote it by RL. So what is RL? RL means actually we by RL we define R with the topology tau, where tau is the lower limit topology. Okay. Now, can you actually prove that this lower limit topology is finer than this topology? How to prove that lower limit topology is finer?
Just use the previous lemma that we just did.
Right. Now it is easy, right? Now can you say that it is strictly finer?
Yes, sir.
Yes, sir.
Why?
Because sir, sir, closed zero open one belongs to second one, but not in first one.
Okay, now can you prove that that is not in first one? How will you
Because
prove that?
first one is only open interval.
No, that is a basis, but why that that open interval do not generate this one? You have to prove, right? You know that in usual topology this is not an open set. We know that, but how? How to prove that?
So because in the second one, zero
But
belongs
every
to the.
union of open sets is open.
No, no, no. That is not the concept. That one the right concept. Who said that zero belongs to this set, but there is no basis element containing zero, which is subset of this. So therefore, this is not open. Did you get? So 0 belongs to this, but there is no a comma b such that 0 belongs to open interval a comma b subset of this. So that implies this is not open. So 0, 1 is not belongs to the top. Okay, so this is the argument you have to give. Okay, but the reverse one is true. Whenever you have x belongs to say a b, the basis element, you can always have x belongs to say x comma b subset of a comma b. Reverse one is true. That's mean this is finer. In fact, the second one is strictly finer. Okay. Now there is another important topology. This is called K topology on R. So K topology on R. Again, it is a clever construction. So first of all, let K equal to that set 1 by n, where n belongs to natural number. So this is actually called K. Now let beta is that collection AB, where AB belongs to R. Now union AB minus the set K, where AB belongs to R. Okay. Now this is a basis. Now this topology, that is that the topology generated by this basis is called K topology on R. Okay, and it is denoted by RK. There was RL. RL means lower limit topology. RK means K topology. It is actually ordered paired R and tau, where tau is the K topology on R. Now, can you compare with RK and usual, say RK and say RU, that is usual topology? Which one is larger, that is finer? Which one is finer?
RK.
RK?
RK.
Yeah, obviously RK looks like finer because it has more basis elements. That's mean it has more elements, right? So therefore that is fine. Now, can you say that it is strictly finer? Yes.
I think so both are same.
Both are same.
Yes, sir.
No, sir, it is strictly fine.
Yes, sir. It's fine.
So can you give me one open set which is in RK but not in usual topology?
Sir, we can take minus epsilon comma epsilon minus k in RK.
Right.
And the
Why
point
do you
0.
do not take minus epsilon? Just take minus
Minus 1
1
comma
comma
1. Ha, okay.
minus k. Now that is in RK. Right? Better to say in that topology tau, say tau k, which is the k limit topology, that k topology. Okay, but this is not in, this is not open in the usual topology. Again the same logic. Why? Because 0 belongs to that set, but there is no open interval a comma b belongs to this. You need to prove that. You need to prove that. Don't say only. You need to prove that there is no a comma b belongs to R such that 0 belongs to a comma b subset of minus 1 comma 1 minus k. You just need that Archimedean property, right? So b is a positive number, b bigger than 0. So there exists a 1 by n such that which is will be less than b. So we are done. Did you get the logic? Complete the argument. This one. Why there is no a comma b? Okay. Now what about RL and RK? Can you compare these two, RL and RK?
No, sir.
No. So can you, so they are not comparable, right? You cannot compare with one with other. So they are not comparable. Now can you give, okay, someone has written something, I think. Oh, no. Right. Now RL and RK not comparable. Now can you give open sets which is open in RL not in RK and open in RK not in RL? Can you give such open sets?
Sir, this same example for RK is not open in RL.
Okay. And RL? and give me an open set in RL which is not open in RK.
Sir, close 0 and open 1, and the point 0 will be point of problem.
Right, but you don't need to take that much, that 0, because see that K, whenever you are using a definition of K, so you have to work hard for the bit point between 0 and 1, right? Just take this kind of, say more than 2, say 2, 3 in RL, right? And then whenever you are talking about RK, so this type of open set will not be there, right? So you can talk about only this kind of open set. Then 2 will be a problem. Or you better to say that 3, 4, this one. Then 3 will be the problem because you need some open interval containing 3, but that is not possible, right? Okay, so these are actually also problems in the assignment sheet as well. So have you tried that assignment sheets? So now you should try, and okay, I should mention you that. So tomorrow is Saraswati Puja. So therefore, Raju told me that he will take the tutorial on Wednesday 10 to 11. Is that fine? Only for this Wednesday.
Yes, sir.
Okay, and then he will continue on Tuesday only. But since this Wednesday, Tuesday is Saraswati Puja, so he will take on Wednesday. Okay, now we have topology, now we know basis, now we introduce another concept called subbasis. Now what is subbasis? So that is a simple one actually. So first of all, okay, we can directly define that. So a subbasis is for a topology on X is a collection of open sets. No, is a collection of sets such that union of all elements of S equals X. Okay, so what is a subbasis? That means subbasis is nothing but only a set, okay, a collection of sets, or you can say collection of subsets of X. You can say collection of subsets of X such that the union of all elements of S is same as X. Okay, so then S is called a subbasis. Now a subbasis generates a topology. Now how a subbasis generates a topology? Now the topology generated by a subbasis is the collection of all unions of finite intersections of elements of S. It looks complicated, right? So what we do, suppose you have a subbasis S. Subbasis means you have a collection of sets, collection of subsets of X such that if you take whole union, that whole union will be X. Okay. Now this is a subbasis. Now how subbasis generates a topology? First you take all possible finite intersections. If you take all possible finite intersections, then you will get a basis. And then you take all possible unions. and then that collection is actually a topology, gives a topology. So did you get this point?
Sir, please explain again.
Okay. So S is the collection of subsets of X such that X is or X equals the union of elements of S. Okay. For an example, you can take S equal to say minus infinity, comma say 2 and say 1, comma infinity. Now if you take only these two sets, this is a subbasis. Is a subbasis of a topology on R. Now if you take say okay, why? Because their union is X. Okay. Okay. Now from a subbasis you can generate a basis. Now let beta equal to the collection of all possible finite intersections of elements of S. Okay, now if you take the collection of all possible finite intersections of elements of S, then beta forms a basis. Now you can prove that as well. Now prove that beta forms a basis. Okay, so first of all, what is the first property of basis? Now take X belongs to X. Okay, now since X belongs to X and we know that S is the collection of all the subsets of X such that X equals to the union of the elements of S, right? That's mean X equal to actually union of some alpha, say S alpha, where S alpha belongs to that set S. Okay. Now since X belongs to this, so there exists some alpha such that X belongs to S alpha, where that S alpha belongs to S, right? And this is also subset of beta because it is a, you can say that S alpha is a finite intersection as well. So that imply X belongs to that S alpha and S alpha belongs to beta. So first property is satisfied. Any problem of the first property?
Sir, here X is all reals, no?
X is?
All reals.
I did not get what?
Sir, real number.
No, it can be any set. I gave one example here.
Okay, sir.
So this is just an example. Okay, so X can be any set. Okay, now we prove the second property of basis. What is the second property? So let X belongs to say B1 intersection B2, where B1 comma B2 are from beta. Now what is beta here? That's mean B1 equal to some intersection of what? It is some I equal to 1 to n, say B, say I. So this type of one, and say B2 equal to intersection of, or you can write only Si, say, and B2 equal to say J equal to 1 to M, say Sj dash, where Si is J dash from the set S. Is that clear? Because we take two elements B1 and B2 and it is from beta. Now what is the beta? You can see, check the definition of beta. Beta is the collection of all possible only finite intersections of elements of S. So therefore each B1 will be in this form and B2 will be this form, therefore this. Now you can check that. Now B1 intersection B2, it is also finite intersection of S only. Right, now this is also belongs to beta. So we have X belongs to now B3 subset of B1 intersection B2, and here B3 is itself B1 intersection B2. So we are done. So the second property is also satisfied. Okay. So therefore, if you have any element, say S, which is just a collection of subsets of X, where X equals the union of elements of S, then S is called a subbasis. And from a subbasis, you can generate a basis by taking the collection of all possible finite intersections of elements of S. And then from that basis, you can generate a topology. So therefore, in short, you can say that the topology generated by a subbasis is the collection of all possible unions of all possible intersections, all possible finite intersections of the elements of S. Okay. Now suppose your S is this one, say A comma alpha comma minus alpha comma B, where A B belongs to R. Now can you tell me this is a subbasis or not? First of all, is this set a subbasis? Yes or no?
Depends whether A is greater than equal to B or not.
No, A, B are all elements. These are
Oh,
all possible.
yes,
This is
sir.
not a finite set.
Yes.
This is obviously right. In fact, you can cover by two elements.
Yes, then
Now can you guess the topology where it generates?
usual topology.
Right. Now can you prove that?
Um, well, any finite intersection we take, it will be um,
No,
either of
not
the
this way. Not go to that direction. See what is the basis element for usual topology? That is A comma B, right? Where A less than B. Now this is can be taken as minus infinity comma B intersection A comma infinity. So we are done. Right? So that's when open interval AB can be written as two intersection of the sub elements element. So therefore that the basis generated by this sub basis is that one. Right? And it generates the usual topology. Now can you give me a sub basis which generates that lower limit topology? Yes.
We can just take closed A by infinity and
minus infinity,
minus
open.
infinity.
Right. Then it will be it will generate that lower limit topology. Anyway, so this is one example which actually I wanted, but anyway, so this is always remember that any basis is also a subbasis, right? But not obviously not conversely. Not conversely. And similarly, any topology is itself a basis. You can say that any basis is a subbasis of the same topology. Okay, similarly, any topology itself is a basis of for the same topology. Right? Now from this, can you guess that? So I think in the first lecture, I think Raju proved that if you have two topology, their union is a topology or not?
No, sir.
Yes?
No, sir.
No, right? Okay. Now suppose you have a topology tau 1 and topology tau 2. Now can you give me the smallest topology containing tau 1 and tau 2?
Indiscrete topology.
No, that is indiscrete topology. No. The smallest topology containing both topology. So that's mean I am asking that say tau 1 is a topology, tau 2 is a topology, right? Now give me a topology which is containing this, and this is a smallest topology.
So that would be the topology generated by having tau 1 union tau 2 as subbasis.
Exactly, good. That is a good one. So that's mean whenever tau 1 is a basis and tau 2 is a basis, sorry, tau 1 is a topology, tau 2 is a topology, but their union may not be a topology, right? But if you take this tau 1 union tau 2 as a basis, and then that basis will generate a topology. Now that topology will be the smallest topology containing both tau 1 and tau 2. Now you should feel this kind of results.
So in the previous example, sir, where you have taken S equal to sir, A infinite minus infinite B. So in that case, sir, does A comma infinite belongs to beta?
A comma infinite, obviously that is a part of beta. You can skip that one as well. It is not necessary you have to take that one. You can skip that one, but it is possible. If you take in beta, then there is no harm. Note that topology is unique. So that's mean whenever you are taking A alpha, right? A alpha should be open C, that is in tau. But you can consider that A alpha, A infinity in beta as well. And if you don't want to consider, then it is also fine. मतलब समझे हो, मतलब तुम इसको बीटा में ले भी सकते हो, नहीं भी ले सकते हो, both are fine. मतलब ऐसा जरूरी नहीं है कि वो बीटा में रहेगा, ऐसा जरूरी है नहीं. अब ऐसे भी जरूरी नहीं है कि नहीं रहेगा. फॉर एन एग्जाम्पल, मान लो कि हमें एक in this case, okay, right now, right, that is a good question actually. Now if I say that beta is a generated by S, if I say that, that's mean that element should be in B, beta, if I say that. But if you want to consider any basis, that does not mean that this one will be in beta. So answer of your question is, if beta is generated by S, then we always know that S subset of beta. In particular, your A infinity will be a part of beta. Okay, as I said that basis may not be unique, but so तुम उसको skip भी कर सकते हो बाद में. मतलब अगर तुम उसको छोड़ दोगे तो अब भी एक basis elements मिल जाएगा. मतलब basis sorry तो अब भी एक usual topology का basis मिल जाएगा. For an example, if we take a new collection B dash, say AB in R, sorry AB such that A comma B in R, and say B minus A that is less than say 2. So we are just writing 2. That means that difference should be less than 2. Then also it will be a basis for the usual topology. Good question. Now ask me more questions. Then if you ask more questions, then it will be clear to you, as well as if there is some doubt to other students, it will be clear for them as well. Okay, any other question? Yes. What's happened? No more questions?